So today I will talk about my previous work. So actually I'm postdoc at Washington University in St. Louis in US, working more about Antarctica now, but before I was in Macquarie University in Sydney, working about Africa. And the goal of the project was to produce a 3D thermochemical imaging of the lithosphere and sublithosphere using geophysical datasets. And today I will just zoom on a little part of the model we produce. So the model we can, if you want more detail about the model we have, you can see is a paper is active now in Nature Geoscience. We're just waiting to be out. And you can see the different co-authors on the project. So the main leader of the method was Juan Carlos Alfonso. And we collaborate mainly for this kind of project with colleagues from De Beers, so Andrew McDonald and Nicole Januska at the time. And the focus was more about looking at the cratonic domain, but because we are doing some 3D imaging on the larger scale, I will just today, with the time I have, just zoom on very specific region. So today we'll talk about mainly about East African Rift. On the left is a map for people not really very familiar to the region. So in a darker gray blue is the cratonic block, so very old and thick lithosphere and cold lithosphere. And in the north of the map is where we have this hot spot from Afar, so the Afar plume. On the right is what are the seismic instruments, broadband instruments in the last 20 years, I would say. There are some more new network now, but basically all the networks in Africa are located along this East African Rift. So what other information we have? So if we use, for example, the geoid, so geoid will give us information about the density within the lithosphere. So here, as you can see, we have a very high value of a positive value of the geoid anomaly around the edge of the Tanzanian craton, and we can go to the north to the Afar region. And on the left is basically the very low value are associated with the Congo Basin. So what we know also in terms of geophysical observation is the lithospheric thickness. So we know this is from the last model we produced in terms of lithospheric thickness. So the definition of the lithospheric thickness here is defined by isotherm. So there are people use different techniques, but here the lithospheric thickness, so the LEB, is defined by isotherm. So as you can see, we have a very thin lithosphere to the north. So where you have the East African, the Afar region, and then around and when we have very thick region is basically where we have the cratonic block. So we recover very well, very thick lithosphere in the east part of the Congo Craton, about 240 and 280 kilometers thick, and we have different blocks in the south with the Zimbabwe and in little block beneath south to the Tanzanian Craton. And as most of people know or doesn't know, I would say, the Tanzanian Craton is a thinner craton, so we have a lithospheric thickness about 180, 200 kilometers beneath the Congo Craton. And I put on the left is the comparison between geotherm, 1D geotherm derived from geophysics inversion. I will discuss later about the method. So these are the lines derived from the geophysical observation. And the green dots, we can see the little green dots, are derived from geochemical analysis, from xenolith observation analysis. As you can see, the xenolith also gives us a little bit of constraint in terms of time, because with geophysical data set, we only constrain the present day structure. And if we are able to get information from geochemistry, we can also constrain the time and compare the evolution between the time of the xenolith and the present day. So for example, we can see that the lithospheric thickness in these two specific regions, so in the south of the top one is in the east, and the other one is the other side of the Tanzanian Craton, are similar. They don't change from today in the last, I would say, 5-10 million years. So no effect on, no changing in terms of lithospheric thickness and thermal structure in this region. So then what about, I will say, the mantle flow pattern beneath the region? So this is an old study from Sabe et al. 2016 on a larger scale, where they produce an azimuthal anisotropy map. So what we map here is the velocity, I will say, shear wave velocity variation with depth, and the line corresponding to the phase direction of the azimuthal variation of the velocity at different depth. As you can see, for the 80 kilometer on the left and 180 kilometer, we have some very different variation. So it means we have a decoupling between the upper part of the lithosphere and the deeper part of the lithosphere around the Tanzanian craton. So if we go deeper, we can also compare the azimuthal anisotropy on the left with what we call the shear wave splitting result on the right. So this is from a recent paper from Adrian Mana et al. 2021. And the shear wave splitting result is information from the anisotropy from the core mantle boundary to the surface. So we have not really concern in terms of the depth, but if we are able to compare the shear wave splitting result with the azimuthal anisotropy from surface wave thermography, we can see the difference between the deeper part of the mantle and the upper part of the mantle. So this is what the seismic information give us and what geophysical information give us, but what kind of information, what the geophysical data set tell us about the thermochemical structure. So thermochemical structure here is in terms of thermal structure, so the variation of the geotherm from surface down to 380 kilometer depth, and the chemical structure is more about the bulk composition in terms of magnesium number. Then, because we know around the Tanzanian craton we have mantle upwelling, so the main one is on the northern part in Ethiopia with the Afar region. So what does the mantle upwelling affect the physical state of the region in terms of temperature and composition? And also what the thermochemical structure can explain the magnesium distribution around the Tanzanian craton, I would say here. So in terms of methodology, what we use here is a John inversion technique and petrological modeling. So what we call in the community is the Litmod Approach. So for given regions, we divide the region in 1D column. So on the right, you have a map and every dot corresponding to one node, and every node we provide geophysical information such as elevation, geoid, and the dispersion curve. So basically, dispersion curves will mainly control the temperature because surface wave is very sensitive to temperature here. And what kind of physical problem we solve here is the steady state heat transfer, the geoid, the isostasy, and the free Gibbs energy to get the information in terms of the bulk composition and the mineral assemblage. In terms of modeling, so we are using a Bayesian inversion. So we generate a lot of model, million of model, and then we just save the best 5,000 best model to provide the final model. And here is the example of the model we have. So on the right, on the left is the LAB depth defined by the isotherm 1250 degrees C, as I showed you before. And the square and the circle there with color coded is the kimberlitic volcanism and carbonatite volcanism. So just keep in mind that the kimberlitic volcanism is often associated with the presence of hotspots from mantle plume. On the middle, we have the magnesium number. So they give you information about the depletion of the mantle. So the composition here and on the Litmod approach is only the information between the MOO down to the LAB depth. So we don't really have that much constraint in terms of composition for the sublithosphere. And here is just an average. So it's an average on the full column. We don't get enough resolution to say what will be the composition of the 10 kilometer by 10 kilometer. So this is very wide, large thickness of composition. But to give you a very good idea about how the variation of the composition with the in a larger scale, which is not possible only with geochemical information. And you can see that the very depleted regions are located where we have cratonic domains, so very thick and cold region. And on the right, we have the temperature at different depths. So you can see how the temperature changed from 50 kilometer depth to 250 kilometer depth in this region.
Walid, you had commented?
Yeah. Okay. So here I just show you what the people, a lot of work was done recently in terms of lithosphere. You can see the other paper from Hu et al. 2018, then Chile et al. 2020, and our recent paper 2022 talk about the thermal erosion at the base of the lithosphere. So this is very common. Everyone are consistent about results about that. But what about the sublithosphere? So we know in this region we have mantle plume, and this is the recent result from regional body wave study by Kenotis et al. In the Turkana Depression. So the Turkana Depression is in between the Afar region in the north and east and the continental craton. So it's where we have, I would say, low topography in comparison to the high topography in the both region. So we know we have mantle upwelling. So this is from the body wave tomography from P and ACE. And what we find using the joint inversion approach in the Litmod is, as we know, we have upwelling, mantle upwelling in the sublithosphere depth. So beneath 200 kilometers down to 300 kilometers for the model. And they are supporting this shoulder around the Tanzania. But what we map in this approach is this forcing downwelling associated with the upwelling beneath Afar, and this forcing downwelling are exactly located where we don't have any volcanism in the northern part of the Tanzanian craton. But if we look at a larger scale, continental scale, we also map similar pattern of downwelling also in the southern part of the Tanzanian craton there. But we don't have trigger force like in northern Tanzania. So in terms of take-home message here, from a, I will say, data perspective, so we show from this approach combining different geophysical data sets that we have a very thin lithosphere to the north of the Tanzanian craton, and the upper mantle is warmer, basically due to the Afar mantle plume. We also show from this approach on this small scale and using, I would say, limited data set, that the asthenospheric control this downforce and the absence of magmatism to the northern part of the Tanzania. So why I say is a limited data set is because our data sets are mainly controlled the 200 kilometer depth, because we use only surface wave tomography. So if we want to map better, deeper depth in terms of thermal structure in the sublithosphere, we probably need to include the body wave, which is more sensitive to deeper part of the mantle there. So in terms of work in progress, so we try to combine the thermochemical structure, what we have today, with more numerical modeling, and try to see also what would be the role of the Congo craton, because the Congo craton is one of the larger cratonic domain in Africa, and how this Congo craton, very thick and cold, control the mantle dynamic in Africa. And this is a collaboration with Anne in your institute. I think I'm done here. So if you have any question, comments, I'm free to ask. Thank you.
Excellent. Thanks, Walid. Any questions? Please type them in the chat or raise your hands. Fola, you go first.
Okay, thanks, Walid. Nice presentation. So the quick question I have is, given that MT is an important part of your input data.
The MT?
MT.
Magnetotelluric, for the moment, we don't include the magnetotelluric, but we can do that because now we are already implemented this part. So if we include the MT, we can have more information about the water content and the melt.
Okay.
And this would be very good for Tanzania and also South Africa, where we have data set there.
Okay, because that was going to be my follow-up question, that in areas where you don't have MT, what do you do? Because I've seen studies that extrapolate across large expanses, big areas where you don't actually have stations. And I feel like if you don't have a station at a location, you really cannot resolve the electrical structure of the crust or lithosphere in those areas. But, yeah.
I will say where you don't have station, because we use a joint inversion, we try to use the sensitivity of different data sets. So it's like region where we don't have that much seismic station, and we combine with gravity to improve the crystal model or the lithospheric model where we don't have that much constraint. Because the seismic station and seismic method are always limited where we have seismic instruments. So where we don't have, we need to use like satellite information. And in terms for the MT1, it's true, will be more complicated because it's smaller scale, but you can improve your resolution on the smaller scale where you have MT and seismic to improve your model on the smaller scale. But if you want to work on larger scale, I guess you need to look at continent where we have larger scale MT, like in Australia and US so far. Yeah.
Sounds good. Thank you.
Makoye, please unmute and ask your question yourself. Makoye, you asked the question in the chat. Can you ask the question yourself?
Yes, please. Thank you very much, Walid, for your very good presentation. In your model, you've shown that below the Tanzania craton, there is downwelling of the mantle. But
it's not beneath the Congo, it's not beneath the Tanzania craton, it's on the northern part. So it's between the Congo and the Tanzania craton. So it's where, if I can back my model somehow. But yes, continue your question. I just need to back to my.
Yeah, but something which I'm wondering, if within the Tanzania craton, I'm from Tanzania, by the way,
okay.
And in the Tanzania craton, we have several hot springs. And so my question is, how can you explain the presence of the hot spring within the craton while your model shows that there is downwarping of the mantle?
So basically where we have the downwelling is basically more this region there. So it's out of the Tanzania craton.
We can't see anything.
Sorry.
See the last slide.
I guess I'm on the wrong presentation there. So basically where we are when we talk about this downwelling process. So the Tanzania craton is there, and the
unfortunately I cannot see. No, I don't know if it's myself alone.
No, I also don't see anything. I still see the final slide.
Give me just a second, then I think I'm just on the wrong presentation. Okay. Can you see my slide now?
Yes.
Yeah, okay. So when we talk about the downwelling process, is exactly in this region, so 2 degrees north. So it's not beneath the Tanzania craton by himself, it's where we don't have volcanism, so it's this specific region. And I don't know if in your case, you have something, you can tell us there are something around, but we don't have any volcanism at 2 degrees north.
Yeah, actually the hot spring is located south of the Lake Victoria.
Okay, so more here where we have
somewhere there, and then in the northeastern part, somewhere
here.
No, within the Tanzania boundary.
Okay.
Yes, somewhere there.
Yeah, so here if you can see it's very depleted. So now we have upwelling. The downwelling part is very at the northern edge there, where we don't have no volcanism in between this region there.
Thank you very much, Walid, because that was my worries, that if there is downwarping, why do we have several hot springs just southern part of the Tanzania craton? Thank you.
In this case, the model would be wrong, but we double check and we have data set there. But no, the downwelling process is sublithosphere and is to the northern part of the Tanzania.
Okay, thanks. We have to come to an end with the questions, but I see that Emmanuel, the next speaker, has a question. I think we should take that one. It's a nice transition.
Yeah, this is actually a comment and rather than a question. So our friend from Tanzania, you really do not need to worry so much because I think there's actually upwelling. From my talk, we will we will actually see that there is upwelling happening beneath the Tanzanian craton, and it's good enough that there are hot springs there. That might explain, and from my observations can explain that. So, okay, let me share my screen and start with my talk.
Yes, thanks, Walid.